In this 7th lecture on quantum Schrodinger equation in 1D, today we shall discuss the quantum mechanics under Dirac delta function. In most of the textbook on quantum mechanics, you will find that the boundary in connection with the boundary condition to be satisfied by the wave function, it is written that psi and psi prime has to be continuous. This is the correct statement. Psi has to be continuous everywhere, but psi prime, that is the del psi del x, may not be continuous everywhere. We have already pointed out that the first derivative of the wave function is continuous only when there is no impulsive force, and in presence of impulsive force this first derivative is no more continuous. Today we shall take an example of Dirac delta potential, that is for a particle moving in one dimension, the potential is given by delta x minus a. So there is a discontinuity of potential at x is equal to a, and the strength of the potential is lambda. That is, if lambda is negative, then it is a for lambda less than 0, this is a well, delta well, and if we have the here lambda is greater than 0, this is delta barrier. We shall write down the wave function for a particle of mass m subjected to this potential and the energy of the particle, let it be E. Then the wave function is time independent Schrodinger equation is this. Where E is the energy eigenvalue, and this, or you can write it we integrate this equation once with respect to x in the limit a plus minus delta. Integrate within limits with limits a plus minus epsilon with epsilon tends to 0. So what we get from the left hand side, minus h line square upon 2m, limit epsilon tends to 0, integration a minus epsilon. So we are performing integration just around the delta well, the point of infinite discontinuity in a function, plus lambda being a constant going out, E being a constant, now let me analyze term one by one. If we integrate this, we will get the first derivative. So we will have, and if we put this limit, we will have minus h line square upon twice m, limit epsilon tends to 0, epsilon tends to 0, psi prime at x between a minus epsilon to a plus epsilon. This is the first term. This part is lambda times psi at a because this is the property of delta function and integration includes x is equal to a, so the function is this. We have used that f of x prime delta x minus x prime dx is equal to f of x prime when the integration x includes x is equal to x prime. So it is x prime. This property have been used. And if we consider right hand side, the wave function is finite. So if we integrate this wave function over dx, we get this is phi and this is x between plus minus a, we get this area of the wave function within this, and since this width goes to 0, the result goes to 0. So this is a minus epsilon and this is a plus epsilon. Here you have a, and when epsilon tends to 0, this part goes to 0, and since the wave function is finite, a finite quantity multiplied by 0 is a 0. So we have 0 over here. If we take this on the other side, we will have minus this will be, this part will be psi prime at a plus minus psi prime at a minus. This is right hand limit and this is left hand limit. Or we can write the discontinuity in the first derivative of the wave function around the delta function is this. If psi at a is not equal to 0, the first derivative of the wave function has a discontinuity, and the amount of discontinuity depends on the mass of the particle, on the strength of the delta well, and as well as the wave function of the wave function at the center of the delta well. So this is our conclusion. So discontinuity in potential is this, and it will we shall require it in the subsequent calculation. Where the potential is this. Now we consider the Schrodinger equation or the quantum bound state of a particle of mass m under the action of attractive delta potential. Since the attractive delta potential, that is lambda, is negative, so we write lambda is equal to minus mod lambda. Bound state means E is negative, so we write E is equal to minus epsilon E. So the Schrodinger equation is time independent Schrodinger equation in such case is minus h line square by twice m phi 2x phi derivative minus we assume the delta function to lie at x is equal to 0. with a is equal to 0. For x not equal to 0, this potential is 0. So the equation is minus h line square by twice m phi double prime as p of x is equal to 0 for x not equal to 0. This is the property of delta function. So we can write this as with the solution of this is, the physically acceptable solution is and this is 0, greater than 0. Now the continuity of wave function, at x is equal to 0, that is psi of 0 minus is equal to psi of 0 plus. This is the continuity of the wave function. Even if under the action of delta potential, the first derivative of the wave function is discontinuous, the potential, but the wave function itself is still continuous. So this leads to A is equal to B. So we rewrite this as A. And coming to the first derivative, arrow will come out, with a minus sign. You note that here we have put the equal to sign, equal, less than equal to or greater than equal to, as the wave function has to be continuous. The first derivative is not at all continuous, so we have written letter greater than or less than sign, not the equal to sign. If we plot the wave function, the plot of the wave function is like this. That is, the wave function in both the regions can be written as minus rho mod x. And if we come to the first derivative of the wave function, then a rho, both are positive, this is a rho, this is minus a rho, and this is the amount of discontinuity in the wave function, in the discontinuity in the first derivative of the wave function. So we can write the two important results, that is wave function and its first derivative. So we get the conclusion is this. This is the conclusion that we have done here. Now we use this property, the expression for the discontinuity. You know that the potential is attractive, so lambda will be replaced by mod lambda. So this expression in the present case becomes psi prime and 0 plus minus psi prime and 0 minus is equal to minus twice m mod lambda psi at 0 by h line square. This part is minus arrow at x is equal to 0, as x tends to 0, this is arrow, minus arrow, and this is minus 2 arrow. And on the right hand side you will have minus 2m mod lambda, psi of 0 is a by h line square. So a goes and minus 2 goes, so we get rho is equal to h line square. This is the value of rho. So it is better to write rho here. H line square. Now we come to the normalization of the wave function and the energy eigenvalues. If we consider the energy values, rho is this, so energy E is equal to minus mod E, as the energy is negative, and minus mod. The definition of rho was, the definition of rho, I have erased it. It is rho square was defined to be twice m mod E bar upon h line square. So mod E is equal to h line square rho square, h line square rho square by twice m. And we have the expression for rho square, and for rho square we write square of this thing, m mod lambda square h line to the power 4, and on simplification this becomes square. So on simplification this becomes minus two h line square. This is the value of energy. And we see that there is a single energy state. Single energy state, it seems to be surprising, because in the case of infinite potential well, we found that there were infinite number of bound states. But while considering finite potential well, finite potential well, we found that the number of bound states do depends on the quantity um. Recall our definition of was A times this, and we said that this is we said that the P is equal to the strength of the potential, P is equal to 2A into V0. This is for finite well, finite rectangular well. bound state, and we match this P with lambda for the for infinite well. So the expression for this becomes mod lambda by H line. Mod lambda is a finite quantity but for Dirac delta potential A tends to 0. For delta potential A tends to 0, that is tends to 0. Since is less than pi by 2, there will be, since less than pi by 2, there will be only one bound state, which is the result thus. So this is not surprising. Rather, we conclude that the number of bound states that is being supported by an attractive potential well do not depend exclusively on V0, the depth of the potential, or on the width of the potential, but on the strength of the potential. Now coming to the normalization condition of the wave function. So we find the energy, we have found the energy, we write energy values here. These are the summaries. This is the single bound state energy. Now we want to normalize the wave function. Now normalization, the wave function should be normalized between plus minus infinity. So the normalization is, yes, we have used these two. Not at all. Normalization. So we write it A modulus square, and the integration is from minus infinity to 0 and then 0 to infinity, which we write twice of this. Using the gamma function. So we find that A is equal to root rho. So the wave function actually becomes for A we write root rho, and for root rho the value of rho is given there. This is the normalized wave function. Now, this is the bound state case. If we want to study the scattering of a particle of mass m under attractive delta potential, then what will happen? For scattering case, E is greater than 0, so this part will be positive. of delta potential. Now the Schrodinger equation will be minus h line square by 2m. Here E is greater than 0. For x not equal to 0, we will have the solution is there to this case is that is, we initialize the problem like that this is the attractive delta potential is located at the origin, a free particle of mass m with energy E impinges on it. So this is psi I, and a part will be reflected from this. This is psi r, this is psi r I, this is r, and a part will be coming to this part, this is psi t, this is the t part. So the boundary condition on it is if we apply boundary condition, we see that a plus b is equal to c. So before going to that, let me first calculate psi prime. This is for ik a e to the power I k x minus b e to the power minus I k x for x less than 0, and this is c e to the power I k x for x greater than 0. The boundary condition is psi of 0 minus is equal to psi of 0 plus. This gives you a plus b is equal to c, and this condition, the discontinuity, we find that on the positive side it is ikc minus ik a minus b is equal to, this part is minus 2 m mod lambda, because we are considering attractive world, and psi at 0 is a plus b. And this is equal to also a plus b. So we see that here the result is twice I k b, and on the other side you will have twice m mod lambda h line square a plus b. If we simplify the result, we find that on simplification we get B by A is equal to I beta I beta and C by A is equal to 1 my I beta. Where beta is equal to, where beta is defined as m lambda. I am skipping the manipulation which you can do of yourself, h cross k. Since it depends on k and k depends on energy, k we have defined k depends on energy, so we will have m mod lambda by h line square, and for k we have h line in the numerator and 2me, that is to say it varies as alpha by root e. Beta has 1 by root e dependence. Now if we come to the calculation of probability current densities, the probability current densities can be calculated similarly, and since on both the sides of the wave the wave vector has the same value, we define transmittance as, or reflectance and transmittance as, reflectance is equal to b by a modulus square, which in this case becomes beta square plus 1 upon beta square, and transmittance T is equal to C by A whole square, C by A whole square, this is equal to 1 upon 1 plus beta square. So we see that R plus T is equal to 1, so probability conservation is there. Now what will be the nature of this graph? To see this we need space, so we erase this part. I have completed this, and this is alpha square by e, because beta dependence is alpha by root e, 1 plus alpha square by e. So multiplying both numerator and denominator, we will have alpha square e plus alpha square, and this part is 1 upon, this is as e is equal to 0, this is 1, and as e tends to infinity, this tends to 0. At e is equal to 0, this is 0, and as e tends to infinity, this tends to 1. So the graphical nature of this is here e, this is one line, r, so for variation of r is concerned, r goes like this, t goes like this. That's all about the one-dimensional motion, bound state and scattering aspect under attractive delta potential. If we use repulsive delta potential, it is very easy to show that it doesn't withstand any bound state, because of the fact that we have here the wave function goes as e to the power rho mod x, and for attractive potential rho will be negative, so the wave function will either blow off on either sides. And so far scattering phenomena is concerned, you see that it depends on beta square. The reflectance and transmittance depends on beta square, and beta square goes as mod lambda square. So by changing lambda by minus lambda, the expression for these two will not change. But it seems to be strange that how a particle can overcome an infinite barrier. Here one has to keep in mind that the barrier is indeed infinite in height but has vanishingly small width. So the physics that is involved is like this. The barrier is so high, but a particle comes there, and due to its wave nature it penetrates within it, and it has to stay within the barrier for a small time and it comes out. So this explains the transmittance through a delta barrier. So that's all about the quantum mechanics under the action of one-dimensional delta potential. The message that I want to give you is that the first derivative of wave function is not continuous always, and if we have an impulsive force or an infinite discontinuity in the potential, then there will be a discontinuity in the first derivative whose amount of discontinuity depends on the strength of the potential as well as on the value of the wave function at the center of the wave. And secondly, an attractive delta potential can sustain only one bound state, not infinite bound state. And this is because of the fact that although the strength of the delta potential is finite, but it has vanishingly small width, and the deciding factor depends on strength times the width. Since width is 0, the quantity is 0, and so there it tends to 0, so there is a single bound state and it's not any surprising.